Kia ora. So what we're going to do is we are going to have a look at the binomial distribution. So the first thing we're going to do is sort of get to know the name. So bi, you probably know the word. Bi just means two. Right, so the binomial distribution is pretty much things that happen when there are two outcomes, but those two outcomes happen a multiple amount of time. So we're going to start off with coins. So we've got 3 coins here. Right, if we had 3 coins and we want to find out like a probability distribution of how these coins could land. So let's have a look. So this one's gone for heads. We've got a heads and we've got a tails. So heads, heads, tails. Right, we know in probability that heads, tails. Right, what is the chances of this happening? Well, actually, let's think first. What are all of the possible outcomes when we are flipping 3 coins? Right, so let's do that. So we got heads, heads, tails. What else could we have? We could have heads, tails, tails. We could have heads, tails, heads. We could have, are these all of the head starting ones? I think so. Then we could have tails, heads, tails. I'm just going to do them repeated. Tails, tails, tails. Oh, I missed that one. Heads, heads, heads. Heads, heads, heads. We could also have tails, tails, heads. Or we could have tails, heads, heads. So this list that I've made, there are 8 outcomes when you flip 3 coins, right? And each of these outcomes has a probability of occurring. So the chance of getting heads, heads, heads is, well, it's a 50% chance, 50% chance, 50% chance, or half, half, half. So half times a half times a half, that's 1/8. And actually all of these have a 1 out of 8 chance of occurring. So how do we build a distribution out of this though? Like, how can we make a distribution? So the way that we can make a distribution isn't, what we can do is we can stop worrying about the order in which they occur. So let's do some counts, right? So how many times does heads, heads, heads occur? This occurs only 1 time. How often does 2 heads and 1 tail occur? So here's 2 heads and 1 tail. Where else is 2 heads and 1 tail? Here. 2 heads and 1 tail. Where else? Down here. 2 heads and 1 tail. That's the other outcomes. We could have 2 tails and 1 head here, 2 tails, 1 head here, and 2 tails, 1 head here. And then finally, we have our triple tails. So in the binomial distribution, we're going to stop worrying about order, and instead we're going to count up these occurrences, or how often, yeah, each one. So let's have a look. Well, so heads, heads, heads would be our first thing, right? This is if you get a triple heads, right? And then our next one is going to be if you get 2 heads. So that happens 3 times, right? And then what's the third one? Then we get the 2 tails, 1 heads. That happens 3 times. We've got 3 red stars over here. And then finally, we've got the triple tails, which happens once. So this is how we're building up a distribution. So what we do when we're talking about this distribution is we label things with a success and a failure. So here we've got heads and tails. So let's just pretend which one's success. Let's say that a heads equals a I want to do it the other way around just because of the order of my distribution. I'm going to say that tails equals success. The reason being I want the amount of successes to increase. So this one here, how many successes do we have? We had 0 successes. In the blue one, how many successes do we have? There was 3 chances, well, 3 times that only 1 success happened. And this red one, see how it's 2 successes each time? So then that would be 2. And then finally, there's only 1 time where you get a triple success, so 3 successes. So on the bottom here, we're building up our counts. And then going up here, we have our probabilities. right? So this is a 1 out of 8, this is a 2 out of 8, and this is a 3 out of 8. Right, so this is what the binomial distribution looks like. So let's have a look at a more professional one. It's going to look exactly the same though. So our probability of a coin flip, probability of each success is 0.5. Right, how many coins did we flip? We flipped 3 coins, so we drag this down to 3. And as you can see, we have that same distribution here. Right, 1 success, then this one, and then this one. It looks exactly the same. Let's just have a little comparison. Voila. Okay, so this is the idea of the binomial distribution. There are 2 parameters. The parameters being how many things are you looking at, and what is the probability of each individual thing happening. Right? So here we looked at the probability of a coin. Each flip is 0.5, and then we had 3 coins. So this is probably a nice example for you to go back on if you are trying to think about what binomial distribution means. Right? We can also do an example with dice, for example. I might do an example with 4 dice. Right? But we're going to have to change the rules a little bit. Right? Because our probability is no longer 50% like in our coin example. So let's introduce a little thing that I like to do with binomial distribution. So I like to think of the binomial distribution. Oopsies, that does not fit. Let's just stick like this. Right, I think of these, I remember fist. So I've got 2 fists. Binomial means 2, so I just remember fist. If there is a fixed number of trials, in our coin example, the fixed number of trials was that there were 3 coins being flipped. That those are independent of each other. The result of one coin is not going to affect the flip of the next coin at all. They are independent of each other. S, the same probability. Each coin has exactly a 50% chance of landing on heads or landing on tails. So the probability that the coin is a success, it lands on tails, is always 50% or 0.5. And T, there are 2 outcomes. That's why we use success or failure. So these are your assumptions for the binomial distribution. Right, so we're going to remember fist. Okay, so how are we going to do binomial with these dice? Right, well, we're going to have a fixed number of trials. So we're going to have fixed amount of dice. So we want 4 dice. Right? Independent. Are they independent of each other? Yes. Each dice that I roll is not going to affect the next dice that I'm rolling. I should say die, sorry. Yep, independent die. And then S, the same probability. Well, yep, every die is going to be exactly the same. I can't control die unless one of them's weighted, but they are not weighted. Same probability. I'm going to say not weighted. And finally, 2 outcomes. How are we going to do this with dice? Because actually a die has more than 2 outcomes on it. So we need to make some way of having success or failure with our dice. So we need to label what our success is going to be and what our failure is going to be. So how am I going to do it? Just like this. Right? Success or failure. So I'm going to call success on my dice. What's the best number? I mean, 1's kind of cool, but 6 is also pretty sick. No, I'm going to go with 1. I'm going to say 1 is success. Right? So 1 is success, and failure is going to be not a 1. This is how we say not in probability. So this is going to be my failure. So this is actually if it's a 2, a 3, a 4, a 5, or a 6. Right? We're going to call that our failure. So let's make a distribution of our dice then. Well, let's have a think about it. So we're looking at a probability distribution. So we know there are 4 outcomes. So the bottom is going to be Well, there could be 0 ones, we could get 1 1, we could get 2 ones, we could get 3 ones, or we could get 4 ones. Yes, that's right. These are the outcomes. And our probabilities, well, let's just, we could do like an experimental distribution, for example, and then we'll just go over to the program. So here, we just rolled, we got 1 1. This one here, we got 3 ones. That's, yeah, pretty cool. This here, well, we can see how likely that is very soon. We got 0 ones. So we're building up like an experimental distribution of these die. We got 0 ones. We got 0 ones again. So what's the probability of getting 4 ones? Well, the probability of getting 4 ones is just 1 over 6, because that's the probability of success, and then just to the power of 4. So pretty unlikely. 6, 36. What's 6 times 36? Oh man, too early. 180. Is that right? 180 plus 216. It's pretty flippin' unlikely. 6 times 216. Oof, man, I'm not in the mood for this. 1200, and then 16 times 6 is going to be, there's going to be a 36 in there and a 60 in there. So it's a 1296. So the probability of getting that is 1 in 1296. So let's just do it. Let's get it. Let's do it right now. Oh, dang it. No, it's 1. Right. So, I mean, we can do an experimental distribution all day, and they will possibly make you do experimental distributions in your exam, but we can just model it on this computer program or on your calculator. Okay, so what we're going to do is our probability's changed, and now it's 1 over 6. And the amount of dice we're rolling is also changed. So this is what the distribution looks like here. The probability of getting, let's look how tiny this is. This is the probability of getting 4, and they found it to be the same as us probably. No, actually, what? That's completely different. Oh, I'm looking at this one. Yeah, 0.0008. Now, what I want to focus on now is look at these orange bars. So this is a cumulative distribution. So maybe the question could be, what are the chances of rolling less than 2 dice? So that would be rolling 0 ones or rolling 2 ones. Rolling 1 1, because that's less than 2, right? So that what this cumulative does is it adds 0 and 1 together to make this bar. So the probability up here would be 0.8681. Now, I want to show you guys how to do that on your calculator. So if you want to do binomial on your calculator, we go into menu, and then we go into statistics, then we go to distributions, we then go to binomial, and then we go to, first we'll test it with a point, and then we'll do cumulative. So we'll start with a point. So let's say, what is the probability? We could change it to variable. So we want to know the probability of getting, let's say, 1 1. So we're going to make that a 1. We're doing 4 dice in total, and the probability of each dice is 1 over 6. Right, that's all good. So our probability is 0.3858. So that's the same as this here, 0.3858. So in our calculator, let's say the probability was, what is the chance of less than 2? So maybe 0 plus the 1. Well, we can do that in cumulative. Over here, binomial, we'll go to cumulative, and then we're just going to change this to being, oh no, it's actually all good, because x equals 1 means we're looking at everything up until 1. So that's x equals 0 plus x equals 1. So we're expecting to get our answer here, 0.8681. There you go, 0.8680. They did far more dp than me. This is only a 4 dp. Alright, so that's pretty much binomial distribution for you. Maybe another couple of details just because we're doing an introduction. Your formula sheet has these. If they ever ask you for a mean of the binomial distribution, it's just the amount of trials times the probability. So in our dice example, the mean would be 4 dice times 1 over 6. So the mean outcome is 4 over 6. So that means that the mean sits somewhere around here, which looks pretty about right to me. Right, then this is the standard deviation. The formula looks complicated. Remember, pi just means probability, so all you're doing is just inputting this into your calculator. Square root, maybe open a bracket in your calculator. Actually, let's just do it as an example, because this is maybe a little bit complicated. So for our one, our standard deviation is going to be square root, then we're going to do a bracket. N was 4 dice times the probability was, I'm going to put this in brackets just to be safe, 1 over 6 times, so that's our probability, or pi, and then, ooh, have I got enough brackets here? Yeah, this should be fine, times 1 minus that probability, or 1 over 6, and then we close that bracket and then close our big square root bracket that we started here. So our standard deviation is 0.7454. Okay, cool. That is all for the binomial distribution. There you go.